we are going to start with a new concept in this class, which is known as radiosity. So, what is radiosity? When you see a surface, let us say when you are looking at a hot surface which is in an enclosure where the side walls are also hot. So, when you are looking at this surface, if you do not have the enclosed side walls, you are going to get some amount of energy which is coming out of the hot surface. This is due to emission, and emission is a volumetric phenomenon. So, because of its temperature, there would be some amount of heat flux, some amount of radiative heat which is coming from the surface, and that is the emissive power of the surface. Depending on whether it is a black body or not a black body, by the introduction of emissivity, you can predict what is the heat flux, emissive heat flux coming out of the surface. So, using emissivity and the Stefan-Boltzmann law, you can say that the emissive power of the surface, which is at an absolute temperature of T, would simply be equal to epsilon sigma T to the power 4. If this is a black body, epsilon is equal to 1 and the emissive power is simply sigma T to the power 4. Now, let us say this hot surface is enclosed by another surface which is even hotter than the surface that we were considering. So, there is going to be some amount of the second surface is also going to emit, the emission will take place from the second surface, part of which is going to fall on the first surface, and we know how to calculate that part of energy which comes from surface 2 that falls directly on 1 by the incorporation of view factor. But that is besides the point. Let us say that we have the surface 2 which is emitting, and this emission is going to strike surface 1 which is emitting anyway. Now, when that happens, if this is a real surface, then, and let us assume that it is an opaque surface. So, part of the energy which is incident from 2 on 1 is going to be absorbed, and part of it is going to be reflected. So, if you are an observer and you are standing just outside of surface 1, what you see coming out as radiative energy from surface 1 is not the emissive power alone. You also have to consider whether or not the surface is reflecting some amount of incident radiation. So, what you see while standing outside of the surface is different from the emissive power or emissive power of the surface. So, what you see on the outside, just outside of the area which is emitting and reflecting all at the same time is called the radiosity. So, the radiosity refers to emissive power of the body and how much of incident emission it is reflecting. So, it is going to be a function of what is the value of the incident radiation and what is the value of the reflectivity of the surface. Together they would give you an idea of the emissive potential of the body, the emission potential of the surface, which is a sum of its inherent emission and the reflection of incident radiation. That is what is known as radiosity. So, whatever I have described so far, if you look at the figure, I think it will become even more clear to you. Is I have a real surface which due to its temperature is emitting. So, this is the emission, and there is some irradiation which is coming onto the surface from another nearby surfaces, and it is going to reflect portion of the irradiation. When you combine these together, if you are the person who is standing over here, you not only sense the emission, you also sense the reflected portion of the irradiation, and this is what is called the radiosity. So, radiosity normally, generally is not equal to the emissive power. For real surfaces. But if the case is such that the surface is not reflecting anything, whatever is irradiated on the surface, it is going to absorb that without reflecting any portion of it. So, which obviously I am not describing a black body in this case. So, for a black body, for the special case of a black body, there would not be any reflected portion of radiation, and emissivity will solely be constitute the radiosity of the surface. So, for a black body, the emissive power and the radiosity are equal, but for real surfaces, the black body real surfaces, the radiosity and emissive powers are different. So, the radiation flux, which is radiosity, is based on the actual surface area, and radiosity is generally denoted by J. If it is spectral, it is watt per meter square per micron, and from the spectral you can find out what is the overall, what is the total value of radiosity. Since this lambda, this denotes the spectral property. So, that is why it is emissive power watt per meter square, power per unit area per micron, since I have this spectral property over here. So, this J lambda for any lambda is equal to 0, it is connected with the intensity as I, the intensity, the spectral, and this contains both emission and radiation. That is the significance of E and R over here. So, I am trying to relate the spectral radiosity to the spectral radiative intensity, and since it is the radiative intensity, it should contain both the emissive part and the reflected part. So, when we are trying to find out so this is directional and spectral, this is directional and spectral intensity. So, now we know how to do this, for how to find out how to perform this. Somehow I need to I need to take this out of this. So, if and once I have this J lambda, this the total emissivity is going to be 0 to infinity J lambda, which is a function of lambda times d lambda. So, once again I'll explain what I have written over here. This is the intensity of radiation. I refers to the intensity. Since I have the lambda over here, this is the spectral intensity of radiation coming from a surface, and since it is coming from a real surface, I need to consider both the emissive intensity and the radiative intensity of this. So, this is the spectral directional radiation intensity from a surface. From this, I would like to convert this to spectral only. So, I need to take care of the direction part over here, and as we have done before, this J lambda should denote the emissive power, the radiosity of a surface of unit area when it is placed at the center of a hemisphere, So, how do I do that? I integrate over all possible theta and phi, and therefore, this would give me the emissive power per unit wavelength. That is why I have the spectral. Once I have the spectral one, then I should be able to find out by integrating it from 0 to infinity what is the overall radiosity of a surface by integrating over all possible wavelengths. The integration, the first integration becomes easy to perform if we assume that it is a diffuse reflector and diffuse emitter. If the surface that we are talking about is a diffuse reflector and if it is a diffuse emitter, that means after the whatever comes out of the surface, it does not have any directional property, and whatever is incident on it after reflection, the radiation has no directional property, then I lambda E plus R does not depend on theta and phi. So, this can be taken outside of the integration sign, and the integration can be performed for cos theta, sin theta, d theta, d phi between the limit 0 to 2 pi and 0 to pi by 2. So, once we do that, we know that the result for that, we have seen it before, the result for that would be equal to pi. So, therefore, j lambda, the spectral radiosity is simply going to be equal to pi times I. This is first relation, and the second relation obviously is going to be j to be equal to pi times I E plus R. This is the overall radiosity and this is the spectral radiosity. But more importantly is the concept that what radiosity is, that it is a sum of these two. The next step which we are going to do is blackbody radiation exchange. What is blackbody radiation exchange? Let us say I have two blackbodies. So, these are all blackbodies, okay, and this has an area AI which is at a temperature of Ti. This has an area AJ which has a temperature of Tj. Okay. So, this is let us say the area vector, and the area vector here is Nj, does not matter whatever be the area vector. So, when an observer sees the blackbody, it sees not only its emissive power, it sees also whatever emission coming from J getting reflected from B, and therefore, it's what it sees coming out as emissions as J I, which should be equal to, we are going to find out what this J I is. Similarly, the emission which is coming out from over here is going to be the radiosity of the object. For this special case where the body is a blackbody, it is not going to reflect anything. So, for this special case of a blackbody, the radiosity and emissive power are the same. Now, these two are blackbodies. So, they are only going to emit energy based on their inherent temperature, not on any reflection from incident from any nearby, from any object, from any other surface. So, for surface I and for surface J, the two blackbodies who are interacting with each other, we know that we have to take into account the radiosity, because that is the actual potential of the surface in terms of its radiative power. Okay, so, it is not just the emission, it is the reflection as well. So, if you think of the emissive power of an object, of a surface, it is the radiosity and not the emissivity. But since we are dealing with a blackbody, the emissive power and the total radiative power, which is the radiosity, they are equal, because the absorption is going to be total and reflection is going to be equal to 0. So, for this case only, since we are dealing with black body, this Ji is simply going to be equal to EBI and JJ is going to be equal to EBJ. So, which tells us that the radiosities are going to be replaced by EBI and EBJ. So, Q I to J, that means rate at which radiation leaves surface I and is intercepted by J. What is this going to be? It is, first of all, the amount of energy which comes out is AI times Ji, because Ji has units of energy per unit area. So, I multiply it with the corresponding area and I get the total amount of energy which comes out of it, comes out of surface I, okay, or the area of the object having area AI, but not all of it is going to strike J. The fraction which is going to strike J directly is Fij. So, this entire thing obviously gives me the rate at which radiation which leaves I is intercepted by J. Similarly, you can write Qj to I as Aj Jj times Fji. So, this would be the radiation at the rate at which radiation which leaves J and is intercepted by I. So, this is the view factor of J to I, and I think these must be clear to you now. So, the net exchange between 1 and 2, net rate of exchange between I and J, if I call it as Qij, would be Q I to J minus Q J to I. That is the net rate of exchange which we would like to find out. So, what is this? This is AI Ji Fij minus Aj Jj times Fji. Now, AI Fij is equal to, we know that AI Fij is equal to Aj Fji, which is nothing but the reciprocity relation, and we also understand that Ji is simply equal to Ebi and Jj is simply equal to Ebj, since this is a black body, and we also understand that Eb for a black body is simply equal to sigma t to the power 4. This is Stefan-Boltzmann law. So, if Eb is equal to sigma to the t to the power 4, Ji is Ebi and Ai Fij is equal to Aj Fji. So, when you put all of them together, what you are going to get is Qij is Ai Fij sigma Ti to the power 4 minus Tj to the power 4. So, if you look at this, I have simply substituted Aj Fji by Ai Fij, which I can write from the reciprocity relation. Ji and Jj I have taken to be Ebi and Ebj, and I know that Eb is equal to sigma t to the power 4. So, this is a very important relation which tells us what is the net rate at which the ith surface, the surface I, is going to receive energy from the net energy exchange between surface I and surface J when both of them are black bodies. So, if I apply this for an enclosure, the energy which surface I is going to exchange is going to be J equal to 1 to N So, this is what obviously you can see this role to be an extension of this one. So, this is extremely important relation which we have done it for the black body, but we will see how real surfaces can be handled. In the remaining time, I will quickly solve a problem. So, this is a cylindrical furnace whose length is 0.15 meter. Diameter is 0. This is open to the surrounding temperature. The curved area is 1. This is your A1 then, which has a temperature 1350 centigrade, and A2, which is this surface, its temperature T2 is 1650 degree centigrade, and this is 300. So, obviously, some energy is to be supplied to 2, some energy is to be supplied to 1 to maintain them at these two temperatures, and they are going to lose energy through this enclosure. Let us say I am putting a hypothetical surface which is A3. Okay. You need to find this is what we have to find out. So, hypothetical surface A3, this is the one that we have obtained. The heat loss, this is clearly I am going to lose some heat from 1 to 3 and some heat from 2 to 3. So, this is the heat loss, and Q, then Q13 would be A1 between 1 and 3 A1 F13 sigma T1 to the power 4 minus T3 to the power 4 because of the relation which you have obtained in just the in just recently, plus Q23 would be A2 F23 sigma T2 to the power 4 minus T3 to the power 4. Now, from the figure that we have done in the last class, it is a case like this where R1 and R2 are same, and you know what is the length, what is the distance between them. So, here R2 and R3 are the same, and you know what is the distance between these two as 0.075 meter. So, you should be able to obtain using the figure from figure for R j by L to be equal 0.0375 by 0.15 over here, and L by R I to be equal to 0.15 by 0.0375. You find out F23 to be equal to 0.06, and F23 plus F21, 2 is this surface, plus F22 is equal to 1. Since it is a plane surface, this is flat surface, this is equal to 0. So, you can find out F21 to be equal to 0.94. Okay. So, F21 is known to you now. Now, from reciprocity relation, A1 F12 is equal to A2 F21. So, therefore, F12 can be calculated after you put the values of A1 and A2, this to be calculated as 0.118. And from symmetry, F13 1 to 3 must be equal to 1 to 2. So, when you do all these, so therefore, you know what is F13 from here. F13 is F12, F12 is 0.118, F23 you have calculated from here, F21 you have also calculated. So, therefore, the total Q would simply be the area over here. So, pi times 0.075 into 0.15, which is pi dl, times F13 is 0.118 into sigma, which is the Stefan-Boltzmann constant, and 1623. You have to be very careful that always the temperature is going to be in absolute temperature in Kelvin, minus 300 to the power 4 plus the second area, which is a circular area. So, it is pi by 4 0.075 square times the view factor, which is 0.06, times sigma times 1923 to the power 4 minus 300 to the power 4, and the value of sigma obviously you can see it is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So, when you do this, the value of Q turns out to be 1844 watt. So, this is a simple example which shows how much of heat is lost by a cylindrical furnace. But if you think of the utility or application of this is very significant. So, any cylindrical furnace, let us say if this side is not properly insulated, it is going to lose some energy, and at this high temperature the energy, the mode of exchange of energy is going to be radiation. So, using the formula, and I have assumed all these surfaces, the assumption here is all surfaces are treated as blackbody. So, all surfaces are treated as black bodies. So, I have in the first part of the class, I have found out what is the exchange of heat between two black bodies at different temperature. So, when you introduce the fraction energy, that means the view factor concept, this is what you have obtained. Then from the figure of view factors, you calculate what is F23, 2 to 3, and once you have F2 to 3 using the summation relation, you can find out what is F2 to 1, because that is going to be important. Not only F21 is going to be important, F12 is also going to be important, F13 is also going to be important as well. So, using reciprocity relation and the known value of F21, I calculate what is F12, and from symmetry I find out what is F13. Therefore, my Q, I have obtained all the parameters required for finding out the total loss of energy. A1 and A2 from geometry, F13 and F23, F13 and F23 we have obtained from these relations. The last thing I need to mention, stress again and again, that all temperatures to be used must be in Kelvin in radiative heat exchange. So, you plug in the values and what you get is the total heat loss from the furnace through the opening, through the top opening, which is exposed to atmosphere at 300 Kelvin. So, this is a very simple case of an enclosure problem in which all surfaces are black, and therefore, you do not need to introduce the concept of radiosity, but always keep in mind that radiosity is the correct potential, correct radiative potential, true radiative potential of a surface, because it takes into account the emissive power as well as the part of the energy which is reflected from the surface itself. So, one emission, which is a volumetric phenomena, depends on the temperature, inherent temperature of the object, and the second is a surface phenomena which depends on the radiative property, reflectivity of the surface. Together they form the radiosity. Calculate what is the radiative heat exchange between two black bodies at different temperature. Invoke the view factor concept, you get a compact relation. So, to apply those relations into real problems, you need to know the view factor, which you can read from the graph for such enclosures. Once you have that view factor, and once you have used the summation and the reciprocity relations, then you will see that you could find all the view factors which are to be used to calculate the net heat exchange from one or more of the surfaces to another, and that is precisely what we have done in this specific problem, where all the enclosed areas are assumed, surfaces are assumed to be black bodies, such that radiosity is equal to the emissive power. What we would take up next class in the remaining two classes or three classes is that when we are dealing with real surface, where the surface potential or the radiosity is different from the inherent emissive potential of the surface due to its temperature. So, we will take the cases of non-black bodies. To be more precise, we will take the cases assuming the bodies are gray, such that epsilon is equal to the alpha, this relation, the Kirchhoff's law, the most relaxed form of Kirchhoff's law is valid. And from there, we would try to form a network of potentials and resistances and try to see what is the current, that means what is the heat which flows between these nodes, each node representing an area of an enclosed surface. So, those are very interesting calculations, and you would see a lot of similarity with electrical technology. The way these radiation problems for an enclosure are treated, which we will do which will start from the next class.